Hello friends, welcome to the channel of Digital to Real. Today we are going to design the overlap sequence detector. This video is in continuation of my previous video on sequence detector part 1. So here is an example. X is equal to, X is the input stream sent to a sequence detector. So it is equal to 1 1 0 1 1 0 1 1 0 1 1. Now I want to detect the pattern 1 1 0 1 1. As it is an overlap sequence detector, so how the output would come? You see, output would be 0 for the first bit, 1 because we found 1 in the one is in the input stream first bit and 1 is the detect pattern also first bit. So 1 1. So I will wait for next one for detect pattern. Yes, 1 has come. I will wait for the next 0 in the detect pattern. Oh, in the input stream 0 has come. Now I will wait for another one which is in the detect pattern in the input stream. That also has come. Now I will wait for the fifth bit which is 1 in the detect pattern. That is also 1 in the input stream. If I see the input stream 1 1 0 1 1 in the beginning. So when 1 1 0 1 1 pattern is detected, sequence detector give the output 1. Then as it is an overlap one, so if you see these two ones, okay, they become the beginning of the next detect pattern in the sequence. If I combine these two 1 1, they become the initial 2 bits of the detect pattern 1 1 0 1 1. So 1 1, then I get 0. Oh, 0 matched with this 0. So 1 1 0. Then I expect 1 to come in the input stream. So it has come. So 1 1 0 1. Then the last bit in the detect pattern is 1. That also has come. So 1 1 0 1 1. This 5 bit has come. So for this particular bit, once it has come 1 1 0 1 1 pattern completed. So output is 1. Again, this last 2 bit becomes the beginning of the detect pattern. 1 1 0 1 1, when the stream comes and the sequence detector detect the pattern, 1 output comes. This is how a overlap sequence detector works. Means there is an overlap of the bits. These 2 bits, though it is the last of the first sequence, becomes the first of the second sequence pattern. Here these 2 ones in the input stream, they are the last for the second sequence but becomes the first one for the detect pattern. Okay. Now, as we are designing a sequence detector for 5-bit sequence, okay, you see the detect pattern is of 5 bits. So 5-bit sequence, we need 5 states. So the finite state machine will have 5 states. First state is the idle state. Idle state is that we have not got any bit of the detect pattern. We have not got the first bit of the detect pattern in the input sequence. So I have put all dash here. And what we are awaiting, what the detect pattern is awaiting, detect pattern is awaiting this particular pattern 1 1 0 1 1. Next state is idle state. Next state is 1. One state. One state means it has received, the input stream has got the first one. Okay. So now we are awaiting 1 0 1 1 pattern to come. If it comes, then the detect pattern can give the output 1. Third state is the 1 1 state. These are the name of the various states. So 1 1. Suppose the input stream has got 2 consecutive ones. Now we are waiting for 0 1 1 to come and the pattern to get completed. Here is the fourth state 1 0 1 1 0. Now we have got the 1 1 0. We are awaiting 1 1 in order to complete the sequence. And then the last state is 1 0 0 1. 1001. So, 01101 has come. I am awaiting only last one to come. We will see the state diagram now. Now, here is the state diagram for the overlap sequence detector, and this is a millistate machine. Okay, millistate machine where the output depends upon the idle state and the input. Now, the pattern which we have to detect is 11011. Suppose first we are in the idle state where we are awaiting the pattern 11011 in the input stream. And let it be like that, we got the first one. Then from idle state we move to the state 1. But here output is 0. Now in the 1 state I received another one. Then I got the 1 value. So I reached the 1 state. In 1 state I got 0. Then I reached 1 state. You understood? 1 we got. Output is 0 here also. In 1 state if I get 1, I reach the 1101 state. Here also output is 0. Now 1101 output is 0. I need another one. 1101, as it is an overlap sequence detector. So 1101. If I get another one, the pattern is completed. 1101, then another one, pattern is completed, output 1 would come. But the last two ones, they becomes the first 2 bit of the second pattern when it has to be detected. So 1101, if I get 1, rather than going to the idle state, where I am going to the 11 state. As this 11 state becomes the first 2 bit of the second pattern to be detected. Here output 1 has come. Now after the 1101, rather than getting 1, if I get 0, that means that the pattern detection loop is broken and we need to move to the idle state, and the output is 0 here. Now in idle state we spoke about getting 1. Rather than getting 1, if I get 0, then I would remain in the idle state only and output is 0. In 1 state I spoke about getting 1 and moving to 1 state. But in 1 state if I get 0, then 10, no pattern, it is not the beginning of the pattern to be detected. So I move to the idle state where I am awaiting the pattern 11011. So here input is 0, output is 0. Here in 1 state, if I get 0, then I go to 110 state. First 3 bit of the pattern to be detected. But in 1 state, if I get 1, then it becomes 3 consecutive ones. So 3 consecutive ones means that I am still not going to the idle state. Please note, because in 3 consecutive ones, the last 2 consecutive ones can become the beginning of the next pattern of 11011 to be detected. So I remain this 1 state itself. Okay. Now I reached here 110. In 110, if I get another one, I move to the 1101 state. But if I get 1100, 2 consecutive zeros, that means the loop of that 11011, that pattern detection has broken. So I need to move to the idle state only. Okay, that loop is broken. So I move to the idle state. Input is 0, output is 0. Now in 1101 state, I said if I get 1, what will happen? The detection of the pattern will happen. But along with them, last 2 consecutive ones becomes the first 2 consecutive ones of the next pattern to be detected. So I go to this 1 state. And if I get 0, the loop is broken. 11010. So I need to go to the idle state and await the pattern 11011 in the input stream. Hope this state diagram is clear now. Generate the state table with output. First one is the present state. This particular column is for the present state. Now this is for when the input x is equal to 0, this 2 column comes. When the input x is equal to 1, this 2 column comes. Here is the present state. For input x is equal to 0, 2 columns are there. Next state and output. And for input x equal to 1, another 2 columns are there. Next state and output. Now let's write the state table. When the present state is idle and input is x, next state is idle only and output is 0. If the input is 1, then the next state is 1 and output is 0. Now present state is 1. If the input is 0, then next state is idle and output is 0. If the input is 1, next state is 1, 1. Output is 0. In 1, 1 state, if I get input x is equal to 0, then I reach 1, 1, 0 input stage. 1, 1, 0 input stage I reached and output is 0. Input x equal to 1. Now 1, 1 state would remain in the 1, 1 state only. Output is 0. Now in 1, 1, 0 state, if I get the input x is equal to 0, I move to the idle state and output is 0. If the input is x equal to 1, 1, 1, 0, I move to 1, 1, 0, 1 state. Next state output is 0. Now in 1, 1, 0, 1 state, if I get the input x is equal to 0, I move to the next state idle and output is 0. And if the input x is equal to 1, next state is 1, 1 and x is equal to 1, here the output is actually 1. This is the state table I derived from the state diagram. Now in order to design the sequential circuit, I need to determine the number of flip-flop required. As we have 5 states, so how many flip-flops are required? 2 raised to number of flip-flop should be greater than or equal to the number of states. So here P is coming as 3. So 2 raised to 3 is equal to 8. 2 raised to 2 is equal to 4. So 4 is less than 5 while 8 is greater than 5. So number of flip-flop needed is 3. Here I am doing the state encoding. First of all, let me do the binary state encoding. Then the idles 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 1 is 1, 0, 0. So binary state encoding has happened. And here, as there are 5 states, 3 states are unused. 101, 110 and 111. They are unused. But here in the design, I am going to use the gray code encoding. What happens in gray code encoding? Only 1 bit changes when moving between the 2 adjacent states. 001, 00, 000, 001. 1 bit change, but here 001 to 010, 2 bit change are happening. 1 is becoming 0, 0 is becoming 1. So in gray code encoding, there is a 1 bit change. Okay, why it is required? Because it reduces the power consumption of the FSM. Now how binary to gray code encoding is done? There is a separate video in my channel. I will provide the link of that. So in gray code encoding, the idle state is 0, 0, 0, 1 state is 0, 0, 1, 1, 1 state is 0, 1, 1, 1, 1, 0 state is 0, 1, 0, 1, 1, 0, 1 state is 1, 1, 0. Okay, now the states 1, 0, 0, 1, 0, 1 and 1, 1, 1 are not used as there are only 5 states, and with 3 bit 8 combination can form. So this is an improved version of the state table where there are 4 columns. First column is the present state, which itself has 3 columns, y2, y1, y0. State encoding. Then the input x, that is the another column where the input x is changing 0, 1, 0, 1 in this way. Another column is next state, where at t plus 1 time, what would be the value of state? That is next state. That is of 3 bits. Okay. And output, here another column. If you see, the inputs are y2, y1, y0 and x. Present state and input, they make the input to the sequential circuit. Now, for 0, 0, 0, 0, what is the next state? 0, 0, 0, 0. These are here also state encoding has done. If you want to make it clear, please put this table also next to this one. You will be able to work on this particular thing. 3 things I have used here. This table is used. And here for each state, gray code encoding for idle state, 000 is there. For 1 state, 001 is there. For 11 state, 011 is there. Just put them all together and you will be able to write this improved state table. You see, improved state table. So 0, 0, 0, 0. Next state is 0, 0, 0. Output is 0. Present state 0, 0, 0. Input is 1. Next state is 0, 0, 1. Output is 0. Present state 0, 0, 1. Input is 0. Next state is 0, 0, 0. Output is 0. Present state is 0, 0, 1. Input is 1. Next state is 0, 1, 1. Output is 0. Present state is 0, 1, 1. Input is 0. Next state is 0, 1, 0. Output is 0. Present state is 0, 1, 1. Input is 1. Next state is 0, 1, 1. Output is 0. Present state is 0, 1, 0. Input is 0. Next state is 0, 0. Output is 0. Present state is 0, 1, 0. Input is 1. Next state is 0, 1, 1. Output is 0. Present state is 1, 1, 0. Input is 0. Next state is 0, 0. Output is 0. Present state is 1, 1, 0. Input is 1. Next state is 0, 1, 1. Output is 1. I want to design the circuit with the JK flip-flops. So here is the excitation table of JK flip-flop. So if QT is the output of the flip-flop at time t, QT plus 1 is the output of flip-flop at time t plus 1. So 0, 0, at that time JNK input would be 0x. 0, 1, JNK input would be 1x. 1, 0, JNK input would be x1. 1, 1, JNK input will be x0. This is the excitation table of the JK flip-flop. Now, from the state table which I have designed, I have added these separate columns also, which is the flip-flop inputs. So, this particular state table I have improvised and I have added column for flip-flop input also. Okay. So, here we got the next state and output. Now, based upon the present state y2 and next state y2 plus, I am writing the inputs of j y2 and k y2, that is 0x. For 0, 0, 0x. For 0, 0, y1 and y1 plus 0, 0, j y1 and k y1 is 0x. y0, 0 and y0 plus is 0, j y0, 0 and k y0 x. So this is how the flip-flop inputs would come, corresponding to the transition from present state to next state for each of the bits of the present state, that is E for the flip-flop inputs. This would look like this. You can do it on the paper on your own. You will get the better idea. Here is the K map for JY2, KY2, JY1, KY1, JY0, KY0. These are the K maps. You see how this K maps has been drawn. So Y2 dash, Y1 dash, Y2 dash, Y1, y2, y1, y2, y1 dash. Here it is y0 dash x dash, y0 dash x, y0 x, y0 x dash. So this is how we have done. Okay. For the unused state 15, 14, 8, 9, 10, 11, I have put the cross. Okay. For the don't care state in the beginning, because those states were, as they were 5 states, so 3 states were not used. So that I have put in the beginning only. Then after that, you see, I have copied from here J, Y2. What are the states? It is 0, 0, 0, 1, 2, 3, all 0. So here you can make out. If you put this here, particularly here for JY2, what are the input combination for which JY2 is 0 and X, you will get the idea. And JY2 is coming as 0, KY2 coming as Y2, JY1 coming as Y0X, KY1 coming as Y2 dash, Y1 dash, JY0 coming as Y0 dash X, and KY0 coming as Y0 X dash. Here is the K map for the output, which is coming as Y2X. Now I have drawn a rough diagram with the flip-flops. You see 3 flip-flops are there, JK flip-flop 1, JK flip-flop 2, JK flip-flop 3. Okay. This is how the connection J is tied to this. This JY2 is tied to 0 only. Okay. KY2 is actually connected to output also. Okay. This Y2 is KY2. Okay, this is connected. KY2 is connected to Y2, and that as a whole goes to the output. Y2 into Y2 dot X, that is the AND gate, and here comes the output. Here JY1, Y0 dot X is the input to J, and K's input is Y2 bar and Y1 bar. Y1 bar I got from Y1, not of Y1 is Y1 bar, goes to this AND gate. And this J for Y0 is coming as JY0 is coming as AND of X and Y0 bar. Here it is going. And KY0 is equal to X1 dot Y0. And the clock is common to all the flip-flops. The final diagram of the sequence detector looks like this. Okay. If you like the video, please share with your friends. Please subscribe the channel and have a very nice day. Bye-bye.